Section 10.3, Geometric Sequences. A geometric sequence is a sequence that has a common ratio, we call it common ratio R, between two terms, and each term thereafter. We also call these exponential functions. An example of an exponential function would be anything that grows exponentially. For example, 3, 9, 27, 81. If we look from 3 to 9, we multiply 3 by 3 to get 9, 9 by 3 to get 27, 27 by 3 to get 81. Or we can look at 9 divided by 3 is 3, 27 divided by 3, or 27 divided by 9 is 3, and 81 divided by 27 is 3. An explicit formula for a geometric sequence is a sub n equals our first term, a sub 1, times that common ratio to the n minus 1. So in example 1, we're going to go ahead and find the 10th term of the sequence, 3, 9, 27, 81. In order to find the 10th term, I know the number of terms is going to be 10, or my 10th term, and that's going to equal my first term, 3, times my common ratio. Again, my common ratio from 3 to 9 is 3. So again, I can take 9 divided by 3 gives me 3. 27 divided by 9 gives me 3 as my common ratio to the n minus 1, where I know n is going to be 10. Going ahead and multiplying that out, I have 3 times 3. 10 minus 1 gives me 9. 3 times 3 to the 9th exponentially is 3 to the 10th. I can go ahead and throw that in the calculator if I want, and it gives me 59,049. Either of those answers would be acceptable. In example 2, we're looking for the explicit and the recursive formula for the sequence of 2, 1, 1/2, 1/4, so on and so forth. So recursively, what's happening? Well, recursively, I can find that common ratio. I can take my second term divided by my first term. So 1 divided by 2 gives me 1/2. Checking that with the second to the third, 1/2 divided by 1 is 1/2. 1/4 divided by 1/2 is 1/2. So recursively, my term is taking the previous term, a sub n minus 1, multiplying it by that common ratio, which is 1/2. And now I know also that we have to tell you where it starts. A sub 1 is going to equal 2. And we know that n has to be greater than or equal to 2 in order for this to work. Explicitly, how does this look? Well, my explicit formula, again up here, we know that a sub n is going to equal the first term, which is 2, and we're going to multiply it by the common ratio, which is 1/2, to the n minus 1. And that's going to give us our recursive and explicit formulas. In example 3, we have a house being purchased for $100,000 and being used for rental property. So since it's being used for rental property, it's going to depreciate for our tax purposes. So for tax purposes, the house is going to depreciate in this case by 7% each year. So what does that look like? Well, if I purchase it for $100,000, this is at year 0. No time has gone by. So it's really not our first term of our sequence. In order to get to the next term of our sequence, or the first term of our general equation, what's happening? Well, I'm going to take $100,000 and depreciate it by 7%. If I depreciate something by 7%, then the value is going to be 93% left. 93% of 100,000 gives me 93,000. My second term is going to be 93% of that 93,000, or 86,490. So at the end of the first year, I have $93,000 value. At the end of the second year, I have 86,490. At the end of the third year, the value will be $80,435.70. And we can continue this out as far as we want. So can we write an explicit formula to find the value of the house after n number of years? So our explicit formula, remember again, is a sub n equals the first term times that common ratio to the n minus 1. Again, we should remember that we're looking after the first term, or our first term of the sequence actually starts at 93,000. So a sub n is going to equal 93,000 times my common ratio, which was 93% to the n minus 1. Some of you may not like that. And if you don't, some of you may want to start with 100,000. Could we write this in terms of 100,000? And we could. If we know that we have 100,000 and we're going to multiply that by the 93%, well, instead of subtracting one off of it, we're simply going to have just to the n power. And that's going to allow us, now if we plug in 1, 93% to the first power is 93% times 100,000, gets us to that 93,000. So in either case, we can use either of these formulas. And it's really preference on which one you want to work with. What is the value of the house at the beginning of the 7th year? This brings up a couple of questions. One, which equation do we use? And it doesn't matter, we can use either one. But what about the beginning of the 7th? If I take the beginning of the 7th was actually the end of the 6th. And our equation tells us something about the end, or after n years. So after 1 year is really the beginning of year 2. It's kind of like the end of January is the beginning of February, kind of thing that we talked about earlier in the year. So how do we find the 7th year? We're actually going to find a sub 6, which is going to be the end of the 6th year. So here I can use either equation from up there, and we'll use both of them just to show you that it's going to work. So we have 93,000 times 93% to the 5th power, or n minus 1. And that's going to give us, as we put it into the calculator, 93,000 times 0.93 to the 5th is going to give us a value of $64,699.02. If I use my other equation, my 100,000 times 0.93 to the 6th, now if I plug in 100,000, multiply that by 0.93 to the 6th, lo and behold, we end up with $64,699.02. So again, it doesn't matter which equation we use, we're going to end up with the same answer. And that's an example of where we would see an exponential growth or decay along with our segment or our geometric sequences.